Hello everyone, I am Verma. I am a research scholar at NIT Trichy, India. Here I am going to talk about a study which we have conducted in the lecture halls to correlate the occupant subjective responses and the daylighting simulation. So what we have done, we have collected the subjective responses of the occupants through a questionnaire survey, and we are trying to correlate their responses with the results of the daylighting simulation. To begin with the presentation, I would like to get your attention on the few stats regarding the higher education system of India. We have right now 840 universities in which 34.6 million students are enrolled, and according to a projection by the 2030, every fourth graduate across the globe will be the product of the Indian university. These stats substantiate the requirement of more number of higher education institutes in India. In higher education institute, the students spend a lot of time in the lecture halls. That's why the design of lecture halls plays a crucial role in the higher education institutes. There are many design parameters for designing a lecture hall, but natural lighting is the key to achieve the performance goals of the students. Studies has proved that in windowless lecture halls, the students are less focused, unsociable, and uncoordinated. So it is necessary to focus on daylighting while designing the lecture halls to enhance the health, performance, and the productivity of the students. The occupants are more satisfied with the presence of natural lighting in indoors, resulting in nowadays many green building rating systems and organizations have started to encourage the annual daylighting simulation to support the better design. So the aim of the study is to investigate the relationship between the human subjective responses with daylighting simulations in the Higher Education Institute of India. For this study, the subjective responses has been collected from the group of architects and non-architect students. So this studies also try to give the answer that is there any important difference between the visual comfort research results obtained from the architects and the non-architect participants. This is the ground floor plan of the selected lecture hall building. We have selected three lecture hall on the ground floor with having three different orientation to perform the annual and point-in-time daylighting simulation. We have collected 207 responses in which 95 students were the graduated architects and 112 respondents were engineering students. The questionnaire was consist of three sections which are concentrating on visual perception, visual comfort, daylight sufficiency, lighting condition, brightness, and glare. The respondents were asked to evaluate the current daylighting conditions as well as the annual daylighting conditions of the lecture hall based on their intuitions and the past experience. The section 2 and section 3 of the questionnaire are based on the point in time and annual daylighting assessment respectively. We have asked the participant to rate these statements on the Likert scale of 1 to 5. This is the simulation process. After collecting the questionnaire surveys, we have modeled the lecture hall building with the help of Google SketchUp and Rhinoceros, and then we have imported into the Grasshopper. To perform the daylighting simulations, we have used the open source plugin that is Honeybee and Ladybug. The illuminance values were calculated for the same date and time of when the participants assessed the study spaces during the field trips. The simulation results were correlated with the participant responses by using the following metrics. For point-in-time simulation, we have calculated the percentage of the floor area which meets the various threshold illuminance to examine the daylight sufficiency or excessiveness of the lecture halls. The illuminance threshold has been divided from 50 to 5000 lux at distinct intervals. For annual simulation, we have calculated the spatial daylight autonomy with the same illuminance thresholds. So these are the simulation results we got for both point in time and annual simulation. We have plotted a box plot for the percentage of area with different illuminance thresholds. As we can see over here, most of the rooms are falling below the threshold of the 300 lux. According to the National Building Code of India, for the lecture hall, they have decided a illuminance threshold of 300 lux. It means that most of the lecture halls are showing a daylight deficiency. After the simulation results, Pearson correlations were calculated to find out the relationship between the participant subjective responses and simulation results. We have noticed that the questionnaire item T2, T3 and E2, E3 are not found any correlations with any of the illumination threshold ranges, so these items are not included in the further correlation analysis. These are the results for the correlation analysis. We have calculated the correlation coefficient for different event thresholds for all the three questionnaire items. Here we have divided the correlation coefficient for the architects and non-architects group. So here we can see the items B2 and C2 were found as the most correlated indicators to predict the illuminance thresholds. The illumination range from 200 to 500 lux has found the most correlated with the architect's subjective responses. In case of non-architects, not even a single questionnaire item correlated with any of the illuminance thresholds. This finding confirms that the expert participants, which are architects in our study, can better predict the point-in-time simulation results than the non-architects. We found the similar results in case of annual daylighting assessment. We do not found any significant correlation with the simulation results in case of non-architects. The illumination range of 75 to 150 lux correlate best with the architect's subjective responses. This findings confirm that the expert participants can better predict both annual and point-in-time simulation results than the non-architects participants. Finally, to find the difference between the point-in-time and the annual simulation results, we have calculated the t-score and the p-values. The results showed a significant difference in mean correlation values between the point-in-time and annual simulation results. This finding confirmed that the point-in-time simulation results correlated better with the participant subjective responses than the annual simulation results. This is the conclusion of this study. So questionnaire items B2C2 and B3C3 were found as the most correlated indicators to predict the point-in-time and annual daylighting simulation results respectively. The illumination range of 75 to 150 lux and 200 to 500 lux were correlated best with the subjective responses of the architect for the annual and point-in-time daylighting simulations respectively. The results of independent sample t-test revealed that the point-in-time simulation results correlated more with the participant subjective responses than the annual simulation results. The expert participants can better predict the daylighting simulation results than the named participants. In other words, architects were able to evaluate the daylighting performance of a space more precisely than non-architects. The authors acknowledge that the results of this study should be tested again in future researches. Still, this study provides a new finding regarding the predictive ability of simulation results by architects and non-architects. Thank you. That's all from my side.